Do you guys know what happens if you accidentally stop a recording and then restart it?
I think it might just be 2 files now.
Oh, okay.
Yeah, it saves them as separate files.
Darn it. All right. Well, either I'll merge it or just upload both. Okay. Not the end of the world. Okay. Let me go back. Okay. Good bathroom break, everyone. Okay. So we are. So I think we're up to bias and variance, right? Question 5. Okay. Let's go on here. Okay. Bias, variance. Yes, this was also very similar to the things that we had before, where you were given several possible decision boundary equation. Well, you were shown different decision boundaries. In this case, you were given potential associated questions, and then for part A, you were asked to sort of match them. So, so here, I think, just intuitively, that's not really even just data science. That's just basic algebra. But, the more complicated thing, right? This is obviously pretty much a linear thing. So you get something like that. This is a concave curve. So you'll maybe see like a squared term, but you look at something like that. This, we're obviously getting something with higher order polynomials. So again, that's, I don't know if there are any questions about that, but that should have been pretty much a give me. And of course, this is clearly associated with overfitting. This is sort of that Goldilocks, looks about right. And here we're looking at underfitting. And that, of course, leads to our next question, which was sort of similar to the practice exam, but was just asking you to sort of talk about it instead of draw it. But, as we discussed, so talk about both the training and the validation error that you would expect to see over time as this model kind of trains to completion. So this is an underfitting model. So here it learns a little bit off the training data, but clearly not enough. So you would expect both the training and the validation error to sort of fall a little bit, but then they largely stay consistent and elevated because it hasn't really learned anything about the training data. So it wouldn't necessarily treat the test data any better. Here, it's learned a pretty good amount about the training data. So you'd expect the training data to go pretty low. The test data, since it's never seen it before, you would also expect it to go low, maybe not as low as the training data, but you would expect both of those performances to be just about optimal. Here, it's overfit, which means it's learned too much about the training data. So here, the training error is going to kind of continue to minimize, go to 0, but then the more you overfit, the more error you're going to introduce into your validation set. And that's pretty much what we had kind of discussed in the practice exam. I'm not, any questions on that specifically?
For B, if we so I kind of just drew graphs, just like how the sample midterm was, because I figured it seemed like a good way to go. And so I didn't really talk about it. I kind of said it'll follow these graphs, and then I drew them. How does that work out?
That should work fine. I mean, we want to see that you know the information. If you do get points off for that, just submit a regrade and say, like, look, clearly I knew this stuff. It's here. I didn't think I had to articulate it. So yeah, you should be fine with that. So then for part C, which classifier do you prefer, and what are the strategies for improving performance of the other two classifiers? So clearly this one is the one we want. For this one, since it's overly biased, we should just sort of continue to train against the training data, improve the loss function, try to minimize my loss function more. For this one, adding some kind of regularization to reduce the complexity of the resulting decision boundary, right? I think that's something we've discussed a lot, but yeah, any questions on that?
Yeah, I have a question. And I think I got it right, except for how to improve the one with high bias. Mm-hmm. And that was because it's just the equation of a line. And so I basically said, well, this is, given that this is a line, that you probably can't get it any better just by continuing to train, because you can't fit a line to a curve. Like, so I don't know if that, I was going off of the equation that was used and the fact that it was a line drawn.
Yeah, again, submit a regrade for that. But yeah, I think, to that extent, we could have said like, introduce a more complex learning model or something like that, but it can't hurt to submit a regrade. We can see about adjusting that.
Okay.
Okay, any other questions on this one? Let me just double check the chat, make sure everything's good. Okay, so let's see. Yeah, so bootstrapping can definitely be a good way to improve performance, particularly if you're dealing with like weak learning models. Bootstrapping is generally a good way because you're just aggregating performance over a number of models. So you can imagine, even if it's like a linear model, you might get a linear model here, a linear model that's more like this, a linear model that's more like this, maybe a linear model that's more like this. And then when you aggregate them, you're like, hey, yeah, individually they're kind of crappy, but then in aggregate, they sort of are averaging out to this nice curved thing that you'd want to do. So that's exactly an example of where you might get something like that. Okay, so question 6. So perceptrons. So we're given 4 points. It's over here. So these are kind of 4 points here. We have x1, x2 values in the associated class. Beyond, so that's how you read it. So in this case, it's kind of flipped, where the column is your data points and your rows are your features and the associated label. So we have those 4 points, and then we have the perceptron thing here. So we have the weighted sum of my things plus the bias term there. And so that may have been the trickiest part of this thing, is recognizing that there is this W0 term here. So there is a weighted term there as well. So I think whether or not you did well on this question probably just hinged on realizing that weighted term, that bias term was there. So then it's saying, again, there's this decision threshold. If your weighted sum is less than 0, you apply a 0. If it was greater than 0, you apply a 1. So then question 1 was, theoretically, can a perceptron sort of correctly classify this data set with proper parameters? Yes or no or why? And so, here's an example where it obviously can. So if we're saying if both of our weights are negative, and then our bias term is positive, and then both W1 and W2 are greater than W0, then we're going to get the resulting thing that we see here, right? Because here we're summing up 2 negative terms, so that's going to be a 0. Here, either of these are negatives, so that's going to be a 0. Here, both of these are 0, but because we have our bias, we have our weighted term that's positive, the resulting sum function would be positive, so that would be 1. So that's how we would do that. Any questions on that?
Sorry, what do you, I don't exactly understand how, W0 is positive, but W1 and W2 are greater, but I thought they're negative.
Oh, sorry. Yeah. Thank you for clarifying. They're greater magnitude, but they're negative. So the absolute value is greater. Yeah. Thank you for clarifying that. Yeah. Sorry, Axel, let me just clarify, because what you're looking at is for these 2 terms here where, one of these is present, but not the other one. And the resulting term is negative. So both of those, we have to say the magnitude of W1 and W2 is greater than the magnitude of W0 to get that.
I was going to add that I'm pretty sure it still works if W0 is equal to 0, not strictly positive.
Oh yeah, you're right. Oh, good call. So actually, even if you hadn't calculated the weight, you would have technically got there. You're right.
Okay, cool. Just making sure.
Yeah, no, you're right. I missed that. I thought it would be a less than or equal to 0 would be a 0, but you're right. The greater than or equal to 0. So you're right. In this case, even if you don't have a bias term explicitly, it would still work.
Can we just give one specific example rather than a general description like this?
For the solution you're asking, or right now talk through a specific example?
Oh, like for the solution.
Yeah, for the solution, yeah, because you were asked. So basically, what you're technically asked is, can this do it? And if so, give an example. So if you gave an example, you answered the question perfectly. In fact, if you wrote what I wrote, I think you'd still get full credit, but you weren't actually technically answering the question because you were asked to give an example that would satisfy the model.
Got it. Thank you.
So yes, actually, if that's what you did it correctly, and I did it wrong just now. But
wait, this question, wouldn't like W1 and W2 being positive and W0 being negative work? Because essentially a line that would work is like x2 equals 1/2 minus x1. And then if you find the weights for that, it would be like W2 is 1, W1 is 1, and W0 is negative 1/2.
So if I'm understanding correctly, I think the problem comes with this decision function here, because your weighted sum has to be, in order to assign the actual label of 0, your weighted sum would have to be less than 0. And to assign a 1, so you'd be correct if I'm understanding you correctly, which I might not be, but if I'm understanding you correctly, you're right to say that would sort of get a clean division, but the problem would be that the classes assigned would be reversed. So, but maybe I'm not understanding you correctly.
Yeah, I think you're right, actually.
Okay, cool.
Yeah.
Wait, Lionel, I had a quick question about this. Because if you take x1 to be like, let's say x, and x2 to be y, and you plot it, you see that the data is linearly separable. And I was just wondering, couldn't you put any weights and it would eventually just keep running until it separates the data? Because wouldn't the algorithm keep trying until, I don't know, I don't remember if I remember perceptrons correctly, but I thought it'll keep like trying to move it around so it classifies it properly until it stops. So wouldn't the weights just like converge to the right ones no matter what you picked, because it's linearly separable?
Yep. So perceptron convergence theorem says exactly that if there is a clean linear separation that is possible, it will eventually converge on it. So yes, you're 100% right to say that.
So couldn't you just like have put any weights here and then just say, you could argue that it'll eventually converge because the data is linearly separable? Because it doesn't ask specifically for like a set of weights that will converge on just one iteration.
So well, technically what we're, I guess, asking is provide an example that would satisfy the model. But I can see what you're saying, that, I guess what the question had intended to say, like, show what a possible final solution for your perceptron would be, not necessarily show a solution. It's asking for, I guess, a final sequence, not an initialization sequence. But if by any chance you understood it that way and you wrote it out that way and said, because I can prove this is linear separable, it doesn't matter what I start at, it will still converge, then I think ultimately, that would be fair and you would probably get points for that. I don't know if that's what you did, but again,
I just thought of that. I should have written it down.
Fair enough. But yeah, I guess the question was technically asking for a for a converged set of perceptron weights. But yeah, I mean, you're right. Any initialization, right? Remember what we said with perceptrons. Perceptrons will, if there is a separation, it'll find it. But, and this actually feeds into B, it won't necessarily be an optimal solution. It'll just be any set of weights that just happen to satisfy, and whatever it hits first, it'll converge on. And so that's why, kind of like a k-means, which actually we lead to in question 7, in both of those cases, if, for k-means, I guess convergence is always possible. For perceptron, if it's linear separable, it is always possible. So they will always converge, but they are sensitive to their initialization parameters in terms of where they will converge. And that was kind of a big theme for problem 7. And then, I guess we talk a little bit about this in problem 6 too. So, but yeah, great questions on that. So, okay. And then, so question number 2, which we'd already talked about, perceptrons do not employ an optimization function. And then we ask, like, why not? And that was really just kind of a conceptual question of what it is about the perceptron model, the way it learns, the way it runs, that doesn't really allow necessarily for an optimization side to it. So the key insight to solving that was just to kind of acknowledge the fact that the way a perceptron runs is if there, as Take-Home and others have mentioned, if the data is linear separable, it will find that and it will converge on a solution. Where an optimization models are important are where there isn't necessarily a perfectly clean separation. And in that case, your optimization, when you're talking about minimizing a loss function, you're trying to kind of minimize the total number of loss. It may be down to 0, but more likely than that, it's a non-zero sum, and you're trying to minimize that. Whereas, with perceptrons, there's no granularity. It doesn't treat one error any differently than it would treat 4 or 5 errors.
I have a question about part A, I guess. If you started with like initializations of 1 for all the weights and like the learning rate, and you just kind of ran through like the perceptron updating of the weights until it converged on a solution, would that also be like a valid approach instead of saying like these like XYZ will work?
So I think that's kind of what Take-Home was mentioning. Yeah. So again, as long as you articulate that, you should be fine, because what we just wanted you to be able to pick up was there was a pattern by which this data could be separated. And so I think if you demonstrate that knowledge, then you should be fine.
All right, awesome.
Okay. Any other questions on this specifically? Okay, Q7, we're almost done. Let's see here. So, okay, so we have 3 one-dimensional data points, x equals 0, x equals 2, x equals 4, which we want to cluster using k-means. And then there's this note that if at any iteration, no point is assigned to some center, this center is not updated during that iteration. So that thing is just saying that if you don't change your allocation of points, you don't update your centroid, right? Once the points attached to a centroid remains fixed, the centroid value itself remains fixed. You only update if a point is either added or removed. Okay, so for k equals 1, compute the local minimizer of the k-means. So again, for k equals 1, all points would be assigned to the same cluster, and then the cluster would just happen to be the mean value of that. Yeah. So any questions on just how you would arrive at that? Okay, seems like everyone's good on that. Okay, we'll get to part C in a second. Okay, so for part B, if you k equals 2, if your initializations are at 0 and 10, what will happen in subsequent iterations? So the interesting things here about this, and this actually kind of bleeds into part C, which is kind of interesting. It's the idea, remember that we said convergence was always possible with the k-means, but it won't necessarily always be the same convergence, and it's not always optimal. And remember, optimal is we look at the sum of distances between the centroid and each point within the centroid. That's kind of considered an optimal thing. So I know there was a question about like a difference between sort of in part C, there's like a global minimizer, and that's really what we're looking at, right? If you think about like local minima versus global minima, local minima says I've hit sort of a stable convergence point, but it's not necessarily the best one. Global says this is absolutely the best we could do if we had full knowledge of our data set. So, okay, so for part B, k equals 2, we start at 0 and 10. So clearly with the first iteration, all 3 points are closer to an initialization point of 0. So they will be assigned to the first centroid. Then that centroid value moves from 0 to, again, 7.3. U2, because no points have been added to it, remains at 10. And then, of course, that centroid value is then stable because everything there remains closer to that value. So, so essentially everything will converge after that first run through into only a single cluster. So again, it's converged, it's a local minimum, but it's not clearly optimal. So for k equals 3, what is a global minimizer of the k-means objective? Is there a local minimizer that is not global? So if we define sort of an optimal solution here as being one in which the sum of the distances between the value and the mean is minimized, then clearly the global minimum would be if each cluster happened to converge on each point. So cluster 1 would be at 0, cluster 2 would be at 3, cluster 3 would be at 4, and the centroid values would be there. Clearly, though, as we kind of already infer for some of the previous things, we can arrive at sort of suboptimal clusterings if any of those values just happen to be arranged sort of further out from the closest one. So again, and we talk about, wait a second, did I write this? Oh, right, okay. Okay, if we initialize our 0. Yeah, sorry, so that's wrong here. Okay, so I think somebody actually called that out. That's clearly not supposed to be 3 out of 5. That should be 7 out of 5. Or sorry, 7 out of 3. Yeah, that's just completely wrong. So because again, the idea here is just similar to point 2, where if you initialize at 0, let's say 10 and 20, that U1, that centroid 1, will then converge at that 7.3 value. U2 and U3 will be unchanged. So clearly that's not an optimal result. And then last but not least, there's a question of like clustering algorithm we would use if we want to learn about clusters arbitrarily shaped and identify outliers in the data. So that was something we had talked about both in lecture and in office hours, but just kind of talking about how different clustering approaches, the strengths and weaknesses of them, and specifically how something like dbScan, because it's density based, it's much better at handling clusters that sort of are oddly contoured or may overlap more linear decision boundaries. Because remember, k-means, because it's just based on relative distance between the centroids, will produce those linear decision boundaries and may end up like slicing, an obvious cluster. If it's like shaped like this, it may end up like slicing it in half, even though what we really want is that whole thing there to be a singular cluster. And then dbScan obviously is also different than like a mean shift in that it explicitly handles and defines data as being outliers. So, whew, okay. That is the exam in a nutshell. Any clustering questions?
If I thought that 0 plus 3 plus 4 I thought that divided by 3 was 3.5 for some reason.
Mm-hmm.
Will that not be too many points off?
0 plus 3 plus 4.
I think I just did 3 plus 4. Like
oh, okay.
I think I did, yeah.
I see. You divided by 2 instead of 3.
Well, I mean, I think I wrote divided by 3 at one point, but I said it was 3.5.
Then that should be fine. Again, basic. I think submit a regrade if you get points off for that.
Okay.
So. Quick question for C. Did you say that that's a typo and the real answer is that the centers should be 0, 3, and 4?
So the wait a second. Oh, 0, 2. Yeah, I'm sorry. Yes, it would be 0, 3, and 4. Yeah. Okay. Yeah. Thank you for clarifying that. So remember, the optimal solution for k equals 3 is each centroid is just centered directly on the value itself, because then the distance between the value and the centroid is 0. So yes. So sorry, it shouldn't be 0, 2, and 3. It should be 0, 3, and 4. That's a typo. Yes. Thank you for catching that. So 0, 3, and 4, which correspond to the actual points. That's the global minimized value. Yeah. Okay, so yeah, thank you for catching that. And then obviously my math was just completely off there. So that would be, again, 7 divided by 3, because just like the other calculations. So, okay, let me stop sharing. Okay, Alvin, I see you have your hand raised.
Nope, I just never left it down from the whole time.
You've just been stretching?
I've just been stretching. I stretch all the time in class, and yeah.
I hear that, man. You gotta keep limber. By the way, just in general, one geriatric to another, you gotta keep stretching, guys. When you're in your 20s, you take that for granted.
You're not in your 20s.
I'm in my mid 30s.
Huh?
I'm in my mid 30s. I'm ancient.
Oh, Leonov.
I'm an elder millennial. Respect your elders. Okay. Any other questions before we wrap up the recording? Okay, Axel, go ahead.
I have a question about project 3. So if anybody has any like questions about the exam, maybe they can go first.
Yeah, okay, good point, Axel. Any last minute exam questions? Okay, Axel, it's over to you. Let's talk project.
Okay, cool. So I feel like this is a question that's been asked a lot, but I just want to like clarify because my models get super low precision, and I think that's something that a lot of other people have been getting. And so what I'm wondering is because of that, it's kind of making my F1 score be shockingly bad, like below 0.3. So I'm wondering if that's indicative that there's something I'm missing, or whether that's expected and it's safe to move forward. And it wouldn't result in getting a bad grade because I don't know, it kind of feels wrong to accept a model that's like that. But also I don't like feel like I know enough to be able to make a judgment call on whether that's acceptable.
You are, for the purposes of this project, that is perfectly acceptable. I would say that in general, it would be good to document that in the report and explain why the model is problematic and things. But yes, I think, I mean, so partially that's kind of on us because like I haven't had time to really work the model myself, so I haven't come up with an effective way of dealing with that class imbalance. So I can't necessarily give you precise guidance on that, but just more generally, you're not going to be graded on the performance of the model. So it's perfectly acceptable in this case to say, just looking at this precisely because of the class imbalance, my precision score is just way off, and that's kind of hitting my metrics, and that's something I have to potentially work for, and that's a shortcoming of the model.
Okay, cool. Thank you.
Yeah. So please move forward with that.
Something I want to add on.
No, you go. You go.
Oh, sorry. I just want to add on to what Axel mentioned, but I was really curious about this as well. And I did a bit of research on my own time and found some papers on models that were used to predict stroke. And I found that their data set was much more conditionally based. So like the data they took were people who were either predisposed to having a stroke or had genetics from perhaps their parents or other factors. While our data set, it looks like it's just the general population. There's no conditional that we're looking on. And I think that's probably why the reason we have such a low precision, just because we're looking at practically everyone in the population.
Yeah. Brandon, I think that's a great point. And just, I guess more generally with data science, one of the, upstream things, right? For this class, we sort of start at you're given a data set and it's what can you do with the data set? But the reality is a lot of the work in data science is the experimental formulation part of it. How do I scope this? What do I define as victory? And a big part of that might be doing precisely what you're talking about, is saying, realistically that the total incidence of stroke in the general population is very low. And so if I'm scoping my model widely enough that I'm basically admitting everybody, I could be setting myself up for a lot of heartburn downstream when I'm actually trying to build a model around that accurately. But something like exactly what you're saying, where you sort of down select up front and you say, okay, I'm going to construct a model that's specific to patient demographics that are already at elevated risk for a stroke, and then use that as my baseline, then theoretically the model can be a lot more effective. And that's a perfectly valid set. Like one of the things that you will note with this is oftentimes when you build models, you will build models for specific cohorts of your population. So I think that's a very good insight for that.
So I just wanted to ask really quick, because I know a lot of people have been asking this like on Piazza and everywhere. But I also asked you before, is the like order of operations in which we do things between like splitting and balancing and all that, will that be taken into account for our grade for the project? Just because there's like a lot of discussion in the group me and everywhere, and people are like freaking out about like I did it this way versus I did it that way. So I just want to like ease people's nerves, I guess, about that.
Yeah, so blanket statement, it'll be fine. And I think that those were some really good conversations that we've had about that, but we have not specified sort of a precise order of operations for that. So you know, if you, let's say, decide that you want to augment your data before you split it, if you decide you want to down select before you split, or, you know, any kind of things like that, we're not going to take off points for that. It's good that you guys are all thinking about that, because that really is critical. It's kind of in that nuance that you can kind of make or break your models, but you know, we get that there's just not enough time to really do this, and you kind of have to whip through it. And so, you know, again, I'm thrilled that that's coming up in discussions, because that is so critical, but it won't affect your final performance.
Awesome, thank you.
I just had a quick question. Wait, I was just about, oh yeah. Is it okay if we only use models from sklearn? Or, because I just realized I totally forgot that there are a bunch of different other libraries I can use for machine learning stuff. Like, I think someone was mentioning like PyTorch or some other libraries. And I realized I didn't even think about like using anything other than sklearn. For example, for like the neural network, I just used like sklearn's MLP classifier, which apparently isn't that good of a neural network.
Yeah, it's kind of being in the, you're just hanging out in the kiddie pool of neural nets.
Yeah.
But no, to your question, you know, again, it's not that old, you know, that metric, the heuristic I use for it, which is like, if we haven't explicitly asked you to do something in the project, you can't reasonably get points off if you don't do it. So again, you were not explicitly asked to use anything outside of scikit-learn. In fact, you weren't even asked explicitly to use scikit-learn for that matter. So no, if you don't, you know, dive into PyTorch or something like that, you're not going to get penalized for it.
Okay, awesome, thank you.
Yeah, absolutely.
Can I ask a question regarding all this? Because like,
Please.
I didn't ever even see any kind of explicit spec. I just saw a data set. Is there a spec posted somewhere, or is it just kind of like free form?
Oh, yeah, there should be a spec, right? You guys have seen this.
Yeah, there is.
That was on
Is that under
CCLE,
week
correct?
8?
Where is it posted on CCLE? Because I was looking for it, I didn't see it.
I think it's on like week 8 or week 7. It says like CSM148 final something.
Okay, I was just basically going off of what like when you guys had come into class and like spoken about it and stuff. So I mean, like, I'm not in the dark, but all right, thanks.
Yeah, let me in the background see if I can't pull it up on my own, and then we can. But yeah, there is a spec for it. It's not, unlike the previous projects, there's no kind of structured Jupyter notebook for it. It's in the form of a Word document. So it's a bit more open-ended and kind of flexible in terms of how you structure your thing. But okay, my Duo isn't working. But yeah, in general, it wouldn't be. There is a spec out there. So, it's weird. My Duo isn't working. In the chat, can anybody see what CCLE like what?
I found it. It's under weeks.
Okay, cool. Okay. Oh yeah, thank you guys. Yeah, for some reason my Duo is acting up. Yeah. Okay.
I had a question about like crossing features for the project.
Sure.
Or more specifically, like I kind of just chose like 2 of the numerical features and multiplied them because I couldn't really find like I couldn't really tell like anything significant to like cross.
Yeah.
So I guess, do you have any like advice on that?
So again, this is ultimately you'll get credit no matter what you do. But what I would say is one of the things I think we'll look for specifically in the report is a discussion of your data engineering strategy. So ideally, you know, you would have a bit more than I couldn't find anything that worked, so I just multiplied these 2 together, right? Maybe at least there'd be some kind of rationale for why that might be a thing. But to a degree, it's you go through the motions with it. but you can just kind of articulate maybe some of the thought process in the report, and you'll be great.
I was wondering for the Jupyter notebook, how much writing should we have in there? Because I'm kind of doing like a similar amount of writing that we had in like project 2, but I'm wondering if maybe it makes more sense to like really cut it down and move all of that to the report instead.
I would recommend the latter, because so here's the thing. You can always, because I think the instructions Orpaz gave was you would submit it all as one big PDF file, I believe. So theoretically, the information is all there, but in terms of like when the graders are looking at it, they're going to look first at the notebook for the code, and then they're going to look at the report for the content. And so, if the content is in the notebook, it's still there. You should still get full credit, but it'll probably kind of involve a regrade request. You have to be like, hey, I actually did cover that. If you look at this section of the notebook, it's there.
Okay, so how much of a narrative should we have to explain what's going on in the code rather than just having like 200 lines of code that are just kind of random?
Yeah, what I would recommend is you clearly label each right there. I forget how many, I think were there 7 specific sort of steps that you were required to take. And so just make sure those are clearly labeled, that you're like, here's where I'm doing step 1, here's step 2, here's step 3. But beyond that, if you think there's any important specific notation, like if you're doing something a little bit unusual that maybe the coder wouldn't, the reader wouldn't necessarily understand, maybe it might be worth adding an explanation. But beyond that, I don't think there's really much else.
All right, cool, thanks.
Yeah.
Oh, sorry, go ahead.
No, go ahead.
I just had a quick question again. So you had mentioned, I think in a couple office hours and maybe in a different discussion as well, that maybe you might want to consider running an OLS on the data to get the p-values and stuff like that.
Correct.
And so I was just wondering, so before I do any of my feature transformations, when I run the OLS, I got like a R² of like 0.3.
Yep.
But then after doing some feature transformations, I got an even worse R² of like 0.1. And so I was just wondering, is that going to be an issue? Cause like, should I like have not done any feature transformation? I don't understand why that would have made it worse.
Yeah. So okay. So the general rule is if you're just looking at the relevance of features to your thing, it's hard for me to put a hard and fast rule on it, but so things like so in terms of feature transformation, so if you're talking about things like one-hot encoding, it potentially makes sense to do it first because you want to look at whether or not those one-hot encoded, those particular parameters are relevant. So if the feature engineering is parameter creation, then it potentially makes sense to plug it into an OLS after you've done that. If it's transformations you're doing within a thing, so specifically things like data imputation or scaling, or maybe any kind of other modifications to existing features, then it isn't necessarily as great to do that, because what you really want is as close to a raw kind of relationship as possible, because you're really looking at just from just a purely basic statistical correlation. How do these feature values align with my labels? And theoretically, the more you kind of modify those inherent values, again through something like scaling, in a way you're kind of doing it. But I don't want to say that that's necessarily like, if you scale your data first, you're not wrong if you do that. And in some ways, maybe it's even better because that's more reflective of the data you're actually going to plug into your model versus not. So I guess I don't have a particularly good answer for that.
Yes.
But the one thing I would say more overarching is that with an OLS, with a classification, in general, you wouldn't expect an OLS to perform particularly well with a classification. Because again, classification, you have your zeros and your ones, and OLS, you're trying to draw a line through it with the rest of your features, some kind of linear thing. And obviously there's going to be some relationship there, but it's clearly not well, right? You're fitting the round peg into the square hole with that.
So then do you think it doesn't make sense? Because like what I did based on those p-values was like, I was like, maybe I should remove some of these features
Mhm.
if they have, p-values above a significance threshold.
Yeah.
So I did this like thing where I found this thing online where it's like you run the OLS and you get a bunch of the p-values, and then you remove one of the features that has a significance level above your threshold, and then you run the OLS again, and then you see what the new p-values are, and you keep doing that until all of your features have p-values that are below a threshold. And it sort of made sense because it left me with features that I kind of thought might be associated with stroke. Like I did some feature crosses like age times like heart disease or something like that. And that was one of the features that was left, or like age squared, which kind of makes sense as well, because you'd expect that, as you grow older, your chance for stroke sort of increases non-linearly. So it might make sense to have that associated. And I was just wondering, because then after doing all of that, it like basically got rid of most of the smoking one hot encoded like things. And I don't know if that like made a lot of sense to do.
Yeah, that is an approach. So there are multiple. There's a whole like subcategory of approaches to feature pruning, and the method that you're describing is definitely one of them. Of of running an OLS, kind of dropping out, running it again, dropping it out, and it does make sense because you're essentially kind of trying to narrow in on the set of features that sort of makes the most sense to the model, and by kind of trimming either the ones that formally were taking up the most ones, or dropping the ones that just seem to be more noise than anything else, right? You can go either way with that trimming. Actually, there are different approaches, but either way potentially works, and that is kind of a well-established method for doing that. We're clearly not asking you guys to do anything more than a single OLS run through, but that is an approach that's taken.
Okay, thank you.
Yeah, absolutely. Okay. Any other project 3 questions?
Yeah, I just had a quick question about the stratified shuffle split in K-fold.
Yeah.
So I found, interestingly enough, when I did gradient boosting classifier, I got some really good metrics. Like I was getting an F1 of about 0.32 and accuracy of like 0.85, far exceeding any other test I had.
Yeah.
But then when I ran my shuffle splits and K-folds, I found that even looking through each individual split, I couldn't match those scores at all. Like not even in the range. My
so
F1
you would get a run through, and then when you tried to do a stratified, and then you would. That's interesting.
Yeah, so I expect the average to go down quite significantly, right?
Right.
But I think I should expect at least one split to be somewhere in the range of what I got that was in the high range value. So do you have any insight as to what this might be the case?
Well, the short answer is, clearly either like the way if you random seeded or something, but like clearly you got this one, you shuffled your data in a way that the model just happened to work really well given those particular distribution of features into your train and test variables. And then, I don't know if when you just trained it, you did any stratified shuffle split or not, but clearly you just happened to get, you rolled the dice and you got a distribution that were particularly favorable for that learning method. But then maybe when you tried to sort of, I guess, correct for sort of random imbalances through both, doing the stratified shuffling and then also, doing your cross validation. Once you corrected for that, it didn't kind of allow that outlier to pop up as easily.
Yeah, I might have just struck an outlier then,
Yeah.
which is a bit sad because I was really overjoyed at seeing those scores. And then once I ran the actual cross validation test, I was like, oh, what a bummer.
Yeah. Yeah, and no question. I think, unfortunately, I mean, that talks to why, your models are so sensitive to permutations in your data, that you may get these random kind of quirks and when you do a train test split that just happen to like perfectly align, and you get these beautiful metrics that just look perfect, but then you change your random seed even slightly and then your performance just collapses. So yeah, I guess for better or for worse, it just shows you precisely why it's so important to cross-validate your results.
Yeah, just more stuff to talk about in my report, I suppose.
Yep, exactly. All right, guys. Any other project questions?